Okay, this is lecture 20. So we are in lecture 20 here. Today we will try to cover remaining topics in short channel effect. After that, from next lecture, we'll start discussion about MOSFET scaling. I think that actually up to today we can cover the most of the contents related to the device physics itself. After that, we will move to how can we optimize our device using the known knowledge. So, well, a little bit different scope for our semester. Well, the first slide is for channel length modulation. So maybe you have heard about this channel length modulation in our previous lecture, like microelectronics course. So at that time, channel length modulation means that if we have source and drain, and here we have pinch off region. So simply speaking, in this case, gradual channel approximation does not hold any longer. So we have to treat the effective length. So although we have still drawn gate length, but under this part, actually it is not working as a conventional MOS channel. So then what is the effective length? In this case, we have to say that if this is the pinch off point of that operation condition, then this should be regarded as the actual channel length. So when we have quite a long channel, actually whether we have this delta L or not does not make any difference to our output characteristics. But when L itself is not that long, in this case, small delta L introduced due to channel length modulation can be a great impact on our device characteristics. So please have a look at these graphs. Of course, I'm not saying that this is the correct one, but in order to just to see the effect of velocity, the effect of channel length modulation, I intentionally calculate the IV characteristics without, means that without. So actually, velocity saturation should be included every time, everywhere. However, I intentionally kicked out this velocity saturation. So the saturation shown here, or the behavior shown here, is nothing related with velocity saturation. In this case, our electron speed is just proportional to our mobility itself. There is no velocity saturation effect. However, still we have a certain behavior, seems like saturation. And if this is really the long channel device, then we expect almost a perfectly horizontal line for our saturation current. However, in this case, we have a finite slope, so that's the reason why there is something not perfectly long channel behavior. And if it is not originated from velocity saturation, what is it? This is attributed to the channel length modulation. But we have to be a little bit careful because, you know, both of them, both means that velocity saturation and this channel length modulation occur together in the same device, and which one is dominant in our case, as you have seen in our previous lecture material. So why don't you just come back to our previous lecture material, and when you have a look at these graphs, so once again this red curve is the simulation result without velocity saturation, only channel length modulation. And blue curve shows the one with channel length modulation and velocity saturation. So as you can see, the effect of velocity saturation is far beyond that of channel length modulation. So before taking just such kind of reduction of effective channel length, this velocity saturation comes first. So that's the reason why nowadays channel length modulation, its impact is secondary in this case, but it really depends on the case. So now let's go to the real world. So this is taken from TSMC's 3 nanometer node. So 3 nanometer node was announced just 3 years ago, IDM 2022. So actually 2.5 years ago it was announced. And please have a look at this left figure. Maybe this left figure is extremely interesting to most of us. I think that this graph is quite typical, and we should be very get familiar with this type of graphs. So x-axis is channel length and y-axis is dibble. So as I told you before previously, when I draw channel length versus dibble, then there is always something like a sharp increase of dibble when we decrease the length. Now you are looking at the state of the art data from TSMC. So here you can see node 16. Node 16 is the very first node, the very first FinFET node of TSMC. So although the world first FinFET technology was introduced by Intel, however, after that Intel announced that FinFET technology, it was quite obvious that FinFET outperforms every other devices. So rapidly, other competing companies tried to follow up the Intel technology, and N16 was TSMC's the very first one. And as you can see here, the length scale is around 30 nanometer, slightly shorter and longer. And you can see that when they reduce channel length, for example, down to about 25 nanometer case, then yes, they have the values like about 40 over 50. The dimension or unit is 50 millivolt per volt. It means that when they apply very small drain bias, they can have a certain threshold voltage. And when they apply, for example, 0.7 volt to this device, then they can have the roll up of a threshold voltage. They will have reduction of decreased value of threshold voltage. That change is normalized by about 0.7 volt. For example, when they use very extremely small drain bias for linear reason. So that is the way quantify the dibble. And you know that when you have a look at this data, you can feel that in this case, maybe good values for dibble, acceptable value for dibble is around some 10 or several 10 millivolt per volt. So in our previous, maybe you remember, in our previous discussion about short channel effect, so we solved the two-dimensional Poisson equation. After that, after some discussion, we have found that the minimum channel length which can survive from this dibble effect is about 2 times, like 3 Tox and WD. So maybe this is corresponding to the lambda scale. So at that time, so we have made a certain assumption. The acceptable value for us for dibble is about at most 0.1 volt What is 0.1 volt? That is corresponding to 100 millivolt, and we assume that the VDD is also orders of 1 volt. So you know that here we have 100 millivolt per volt, and this is quite a kind of quite bad value. We cannot live with this high number, so we wanted to reduce it as much as possible. So, and when you have a look at this number, so this is really well controlled, under 50 millivolt per volt. Now let's go to N7 node. So N7 node, that is already much matured. Between these two nodes we have, for example, N10 node and other intermediate nodes. And when you have a look at this one, well, the peak value, the last value we reported here is a little bit higher, but that doesn't matter. Actually, when you have a look at the channel length, wow. So the length, the maximum length shown here is about 22, and the minimum length was 25. And even in this case, with this even shorter length, channel length, their debug can be controlled about just 30 millivolt per volt. So although gate is even further reduced, so we expect that since channel length is much shorter, so now we expect much higher short channel effect. But they anyhow even suppress this high debug to the acceptable, quite good level. What was the magic? So between this N16 and 7, they succeed to reduce the thickness of silicon. So thickness of silicon is corresponding to the value like depletion region shown here. Not exactly depletion region. Please note that our previous discussion for planar devices, and in this FinFET device we will see later. However, in this case we have to have different terms, but anyhow this is corresponding to the thickness of our silicon. So simply speaking, by reducing the thickness of silicon, we were able to control the debug as much as possible. So as you can see in this case, for example, even when we go down to 15 nanometer, wow, still our debug value can be suppressed below 60 millivolt per volt. So that is really great job. So, and where are we now? We are currently, as of 2025, we are in the era of 2 nanometer node, because there is a time difference between 2022 and 2025. They are fabricating now 2 nanometer node, and this 3 nanometer node is the last FinFET node. So down to 3 nanometer node, they fabricate the FinFETs. After that, they move to different architecture. We will talk about it in this lecture. But when you have a look at this number, so now the number, sorry, this is not 15, but this is corresponding 16, and now we are in the 14, the physical channel length. Although it is called as 3 nanometer node, however, its actual gate length is about 14 nanometer. Well, anyway, this is the convention nowadays. Although physical length is much longer, but they just name their technology following certain naming conventions. So we believe that this is corresponding to 3 nanometer node. And as you can see, still we have the values like around 60. Well, is this acceptable or not? I don't have the real idea about whether this is really good or not, but they say that this is optimized. So yeah, and when they say non-optimized fin, so LED one shows much higher values for dibble. So simply speaking, we cannot live with this such kind of a high value of dibble, and well, this value would be more or less acceptable to us. So this is quite important graphs we have to remember. So what we wanted to do, device engineers wanted to do, is when they introduce a new technology, they wanted to reduce their gate length. Why they wanted to reduce the gate length? Gate length is a component which determines so CPP. So what is CPP? Contact poly pitch. In this semiconductor industry, the word called as pitch is the distance between the same pattern. So simply speaking, CPP means that its original meaning. So now we have certain line and certain lines, and please note that this is the top view. We have a wafer, and in a wafer we have two parallel lines corresponding to gate, and this is for gate. Previously we used polysilicon, polycrystalline silicon to fabricate gate lengths. That's the reason why when we say CPP, this P is corresponding to poly. Poly means that polycrystalline silicon, and this is corresponding to actually at the time gate. So simply speaking, CPP means that contact gate pitch, the distance between gate is corresponding to CPP. Then what is the actual value shown here? Is this the distance between these two lines? Actually not. The pitch in this case is the distance between the same pattern. So we have to have this length as a pitch. So the left end of our gate pattern, and once again the left end of our gate pattern, or usually we just take the middle of a gate pattern and another middle of a gate pattern. They are taken as the reference plane for our pitch calculation, but which one is the reference, that doesn't matter, because when they are periodic, then every position can be used as the reference plane. So anyway, CPP is the most important one to determine what? Determine the area of a certain logical gate, because when we try to make such kind of inverters or NAND or something like that, we have to place MOSFET and PMOSFET, and we need many of them. So they are placed in a same plane, and when we try to place them, the minimum distance between one transistor, so for example, here we have one transistor and another transistor, is given as this CPP value. So minimizing CPP is directly related to the reduction of chip area, because the unit gate can be reduced in terms of area. So that's the reason why we always wanted to reduce the channel length. So CPP is not only a function of LG. So let me just explain a little bit more. So usually when we have a transistor, this is the way we draw transistor. this is top view once again. This horizontal line is corresponding to channel material, for example silicon. There is a long silicon line, and there is another vertical line in this scene. So this is corresponding to the gate metal. Then silicon covered by gate metal. What is this? This overlapping or intersection between these two lines, this is corresponding to the intrinsic MOSFET channel. So this is the channel region, and here we have, for example, source, and here we have a drain. And if we have another gate line running in this case, and this is another transistor. In this case, this is also working as a source or drain, and this is working as a source or drain, and here we have a gate. So now you can see already we are looking at we are now looking at two transistors serially connected. There is one transistor and another transistor, and they are serially connected. This is the way we fabricate several devices into our silicon chip. So please think about the case where we wanted to make the smallest structure we can make. In this case, the CPP would be given as this distance. So when we say that this is a CPP, contact poly pitch, then how can we decompose it into different components? For example, starting from this middle point of our gate metal, we have to go half of gate length. Now you understand this is corresponding to half of gate length, and also here we have half of gate length. So there are two copies of half gate length. So CPP will have just a whole of gate length. And now we have the length scale shown here. What is it? This is corresponding to the length of a source and drain. But in reality, so please be careful. So if we make it just this way, so please think about this one. If we introduce gate, this is metal covered, and if we have source and drain, although this is not contact, but let's say that they are contact, then there is no separation between these two metal parts or two different contact parts. So although this is not contact, but we wanted to usually introduce a certain separation between this gate and actual source and drain. There is a certain length scale, and this length scale is corresponding to the length of spacer. Spacer means that a dielectric layer to separate between two contacts. So usually when you say spacer, that is a kind of silicon dioxide or silicon nitride. Those kind of well-known dielectric materials are used to separate our contacts. So here we have a spacer. After that, we will have the real source drain length. Of course, spacer existing here and there. So when we write down this value, actually we have to write down so L plus 2 times L times L spacer, this length scale twice, and the length of source and drain. That will be the component to make the CPP. So up to now, more or less, the trend was the length, gate length, and actually although I wrote down source drain length, but usually we introduce just half of it as the real source drain length because well, so anyway, so therefore we just call it as 2 times L source drain length. So usually what we have is this gate length and source drain length. They are in same order or same magnitude. So when we reduce the length scale, then following the same scaling rule, also source drain length was reduced. So that's the reason why this one was the key component to reduce this CPP value in a previous decades. So we will see it later in our lecture, maybe in the next lecture. But point is, after time has passed, now reducing this length scale becomes too difficult. Making even shorter one, that is becomes really difficult. So that's the reason why nowadays people give up, and instead of just connecting this number and that numbers, so they individually reduce each of it. So currently, where are we now? So I'm just coming back to our main discussion. We are in the era of 2 nanometer node, and that is corresponding to the length scale, physical gate length scale about 12 nanometer or up to 14 nanometer. 12 nanometer is regarded as more or less understood limitation, the minimum length scale we can achieve with this technology. So there is a consensus of we cannot go shorter than 12 nanometer. So then how can we actually reduce this length scale? For many years, instead of keeping this L value as a certain number, then people try to reduce this source drain length scale further and further. Then although the channel length is kept as the same, but when we just have a look at the unit size of our transistors, anyhow they have been shrunken because anyway the CPP is a combination of gate length and spacer length and source drain length. But if any of them contribute to small quantity, small value, then overall it seems like the technology has been shrunken so considerably. That was the situation. So nowadays, previously, there is plenty of room for source and drain, and only gate was tightly scaled because even at that time, people always complained about the difficulty of scaling. Oh, scaling is too difficult. We are at the end of scaling era. Every time they complained, but from the viewpoint of 2025, they lived in a happy times because their actual device was relatively simple, and their difficulty, technical challenge was not as severe as ours right now. Of course, they have a limited capability and limited experience. We have to understand. So anyway, so that was a situation up to these days. So we have enjoyed the reduction of source drain length. But where are we now? Now the reduction of source drain length really hit the wall, so we cannot reduce it any further. So now people have to come back to once again the real essential question: can we reduce the length? Because this one did their best and reduced quite a lot. Instead, channel just stay there. Oh, 12, I cannot reduce it further because then there are so many list of problems included the short channel shorter than 12 nanometer. We have a long list. So no, I cannot reduce the channel length any further. But now we have to ask ourselves once again, there is no other way. Only the way is to reduce a gate length. Then what can I do? So then now come back to the importance of our previous discussion. Short channel effect is controlled by the thickness of our vertical thickness of our system. So if this one is not reduced severely, then we cannot reduce the length scale any further. That was the situation. So now we have to find the way to reduce the effective length scale further. And that is the main driving force to study alternative channel materials. Because people believe that, well, up to now, for last few nodes, well, source and drain engineering played a great role, and they contribute quite a lot for successful next generation technology development. However, it's now time to reduce the channel length, the essential part, the intrinsic part. Once again, in this case, we need something can have thinner than current silicon technology. That's the reason why people talk about two-dimensional material, which is atomistically thin. So we can make extremely thin system compared with silicon technology. So that is the real issue every day occurring in the industry, and we are currently spending tremendous effort, research and development effort to build new technology. So it is very interesting to all kinds of this complicated effort is related with this quite a simple argument. In order to suppress short channel effect, we must have thin system. Why? Because we must solve two-dimensional Poisson equation, and for two-dimensional Poisson equation, this vertical length scale actually determines their boundary conditions. So when we have a thin system, then actually lateral variation of electric field also can be maintained within quite a short distance. That was the main motivation of all kind of this long journey to find out new technology. Well, so anyway, now you understand the situation is now, although the gate length is stuck to about 14 nanometer scale, but people has always a strong desire to reduce it down to, for example, 6 nanometer. Wow, if we can reduce it down to the 6 nanometer, so without sacrificing anything, the current value of CPP value is about 45 nanometer. So let's assume that we can make it to 6 nanometer. Then what will happen? Without sacrificing anything, if we down it from 14 or let's say 14 nanometer down to 6 nanometer, then there is a number 8 nanometer reduction. Then we will have 37 nanometer. So, well, 45, 37, what does it mean? Actually, in this semiconductor industry, 45 and 37, this is corresponding to 8 nanometer reduction, and this is almost corresponding to 20% reduction of one single length scale. This is a really huge reduction. So I cannot believe actually that can happen in the near future. But so if we have, for example, 1 micrometer, then 8 nanometer difference, that doesn't make any sense. 1 micrometer and 0.992 nanometer. That doesn't make any sense in our actual operation. But in this case, 45 down to 37, that is really big deal. And this is corresponding to a few generation gap between different technologies. This is a really big deal. So that's the reason why people are eager to reduce the length scale as much as possible. So then we wanted to go to this way. So however, the dibble is really the showstopper. As I told you before, can we make a 6 nanometer technology? Can we make a 6 nanometer long channel device? Yes, currently we can build a transistor with 6 nanometer long channel. However, what happens? In that case, actually, dibble will just explode and we cannot use it as a transistor. When we increase the drain voltage, then it is just regardless the value of gate voltage, it conducts. So it is not a transistor at all. So that's the problem. But we are currently working on it. So now let's go to the right hand side figure, and yes. Here maybe you can find that this graph is a little bit unkind, because fin bottom CD. So fin bottom CD means that please note that this is the last fin fat, and here we have the side view. This is a wafer surface, this is wafer, and from top we can see a fin corresponding to the silicon channel. And here fin bottom CD means that CD here is a critical dimension. Simply speaking, just length. So here fin bottom CD simply means this length scale. This is corresponding to fin bottom CD. Then you can ask me this question: why it is called as a fin bottom CD? Is there fin top CD? Yes, you have it, because although I draw just like a rectangle, in reality this structure is made by a certain etching process. So this angle is not a right angle. Usually we have a tendency to have this kind of a degraded fin shape. So usually bottom CD is longer, and yes, so top CD is shorter. So now bottom CD is shown here, and what is the actual value? Well, I cannot disclose it to you. They are just reference value. Unfortunately, nowadays in the semiconductor industry, this kind of information is too precious to have the optimum value. They have to spend tremendous dollars on it. So they never disclose the actual value. So unfortunately, as students, maybe it is not that much. That sounds good, but anyway, there is a certain reference value. And now let's go to this direction. So when we go to this higher value of a bottom CD, what does it mean? Previously, in the reference value, we wanted to build, for example, certain fin shape. And when we go to this plus one case, now we wanted to build a fin which is a little bit thicker. So 1 nanometer thicker than its reference value. So then please try to think about what will happen to these two cases. black case and lead case. Black case, we have very thin silicon, and lead case, we have a little bit thicker silicon. So in terms of dibble, which one is beneficial? Which one has an advantage? Of course, as I told you again and again, thin system, thin structure is much better than dibble controllability. So please have a look at these blue dots here. Blue dots are corresponding to dibble, and when we go to wider and wider fin, then dibble is increasing. So maybe you can feel that, oh, then we have to reduce bottom CD as much as possible. Simply speaking, we have to have a very thin channel. But what happens if we further reduce it down to, for example, minus 0.5 nanometers? It means that compared with its reference value, we wanted to build even thinner device. Well, when we make an even thinner device, then you can see that when we reduce, for example, this is not exactly minus 0.5, maybe just to, I think that well, there is a small difference, about a quarter nanometer, and when we have this small difference, and you can see that the dibble is reduced about 5 millivolt per volt. This is a huge reduction. Wow, good. But why we cannot take it as a reference value? In this case, now please have a look at this lead dots. Lead dots is corresponding to LER. So in this case, line, edge, roughness. So now, since the structure is so thin, so we cannot fabricate a flat line. So let me just show it to you. Magnify, and yes, you can see it more clearly. Here we have two different images. One for very thin structure, and one with relatively thicker structure. So here you can see a little bit white line, and these two white lines just shows the boundary of our FinFET. So when you have a look at this thicker one, you can find that this relatively white region is just a straight forward. Well, here you have the straight line, and when you have a look at this relatively thin case, how does it look like? It's like just a wavy shape. So you can see that. It is not completely random, but it's like a and some such kind of smooth curve, long range variation of line width. This is current limitation of our fabrication technology. TSM's guys are real experts on fabricating devices, but that is their best when they try to make a certain structure. So, well, then can we live with this kind of LER? So roughness? Well, sometimes, but please note that if we have a thinner case, then it is corresponding to the change, severe change of threshold voltage. Also, if we have the thicker one, that part introduce relatively weaker against the Schwarzschild effect. So this variation is really a bad thing. We have to avoid this variability as much as possible. We really hate this variability because we have to build these patterns billion times, several billion times we have to make these patterns, and if each of them shows a wavy shape, well, that just destroy our entire chip. So it never works for real fabrication. So now that's the reason why now we have to stop here, stop this reference value. If they can make it really flat line, even with this thinner fin, maybe they would do that. But unfortunately, the way to make a FinFET is mainly by etching process. Etching means that we introduce certain chemical component into silicon and wait for a while. Then there is a certain chemical reaction between chemical component and silicon substrate, and surface of silicon is just etched away. So that is the way we make this FinFET structure. So in this case, controlling fin thickness is extremely difficult. So that's the reason why, actually, that's the reason why we are now see the end of a FinFET era, because fin should be defined as an etching process, and etching has the limitation to control their fin thickness. We need better way to control thickness, and that was proposed by different fabrication process. Okay, so I spent almost 50 minutes for one slide, but I think that this is really important. This is a real one, just 2.5 years ago, and we are now in these values. And as I told you before, the CPP is not a simple function of channel length, but it also have a severe contribution from source and drain lengths. So when we have the distance between gate and another next gate, of course we have to have this source drain length. So let's say this is a silicon channel and this is a gate, and when you go to in this way, eventually we have to have a certain metal BR. So well, I will explain later if we have chances, but anyway, this is the structure. So this part, these two BR should be regarded as the actual externally available source and drain. This is the metal, and of course between this metal and this channel, and here we have actually just silicon. So although this silicon part is highly doped, so it has quite a high doping density, but compared with this metal, actually our doping density is not that high. So think about this one. When you have a number, doping number, like 10 to the 20 per cubic centimeter, you feel that this is a quite a high number. Wow, I love it. However, compared with the number of electrons in, for example, copper, that is much several orders of magnitude lower than that. So when we make a comparison between electron mobility of copper and silicon, actually silicon has not that much bad. Actually, when you think about metal, the conventional thought about metal is, oh, that is quite much conductive, good, perfect. However, their good conductivity is not originated from their high mobility. No. The reason why they have extremely high conductivity is they have quite a high electron density, mobile carrier density. So simply speaking, so although we have silicon, and silicon is highly doped as much as possible, however, compared with metal conductivity, this is still finite value. Oh, okay, this is a finite value, and they contribute the real finite resistance. So when we model our transistor, then actually we have to draw in this way. Let's say that this is metal, this is Br and Br, and now here we have highly doped source drain region. So this is for example M plus in the case of M MOSFET, M plus and M plus, and here we have now gate. The conductivity shown here, this is controlled by our gate source voltage. Yes, we have studied up to now. But point is, when we say the drain to source voltage, the voltage difference is actually applied between this external terminal and another external terminal. Up to now, we have assumed that the path from this external source to the starting point of our channel, and also external drain to the end of a channel at drain side. These green passes are extremely conductive. That was the assumption we have made up to now. But in reality, especially when we make a short channel device, then this component and that component cannot be neglected at all. So think about this one. You have a small resistance, large resistance, and small resistance, and you measure the resistance of the entire system. Then what is the expected value of your measured resistance? That is just determined by this large one, because you know they are serially connected, and biggest one will contribute most. But now think about this one. Instead of that, now we have one resistance and more or less a similar resistance and more or less a similar resistance. If we have three similar resistances, then what will be the overall resistance? This is not solely determined by this central part. Now we have to consider contributions from this left one and right one. In the case of our MOSFET study, this part is corresponding to the resistance coming from our channel part, and left one and right one is corresponding to the one from source and the one from drain. Don't be confused. These RS and RD are not intentionally added. In order to make our transistor, we have to introduce highly doped region called as source and drain, and itself contribute a finite resistance. So this is unavoidable component. So it is not related with the one intentionally added to fabricate our device or our circuit. So now please have a look at this support. So nowadays, this is so now engineers, device engineers are doing their best to minimize the size of our transistor as much as possible. So now you can see the one over there approach. This is taken from the same paper, TSMC IDM 2022 about 3 nanometer node. And please have a look at these ones. Here we have a gate, and this is another gate. So if I ask you, please draw the CPP, then what is the CPP in this case? So of course, if we have to find out CPP, then we have to find out the middle of our gate and middle of our gate, and their distance is corresponding to the CPP value. Well, good. And now this yellow one is corresponding to metal contact, like source or drain. It depends on your voltage. And in this case, we have to place in this way. If we place contact in the middle of these two devices, gate 1 and gate 2, it's okay. But if there occurs a misalignment, then now you can see that what is the difference between this and that, this and that. Now this yellow part is a little bit shifted to the left side and attached to this G1 device. Then what happens? Now you can see that this yellow line is source drain metal, and this gray one is gate metal, and they are touching each other. What does it mean? They are not isolated at all. So the reason why we have this kind of problem is for current technology, this distance is just 45 nanometer. So since the overall size is 25 nanometer, and please note that once again, if this is 14 nanometer, and this is corresponding to 7, and this is corresponding to 7. Now we have 14 subtracted from 45, so now we have just 31 nanometer for placing our source drain metal precisely at the middle of this 31 wide structure. And if we make any offset or shift of this placement, then there can be happen such kind of isolation issue. So they introduce different ones, but this is not the main topic, the reason why I'm showing you this one. Right now, the room for your source drain metal is just orders of 20, 30 nanometer. Within that short range, we have to introduce our metal and make it to external world, exposed to external world. So now technology is highly advanced. So anyway, although I'm afraid that actually I have not stressed the importance of this source drain part or source drain resistance sufficiently. Although when you think about our lecture contents, up to now I spent quite a long time about the basic operation of transistors. Yes, now you understand part of it. So, and you have spent some lecture hours to study about what will happen if we reduce the channel length. However, in reality, nowadays, this source drain resistance is one of the key components to limit our device performance. Even though we can reduce this component as much as possible, internal transistor, however, if we have quite a high resistance, then we cannot increase the overall current. So let me just show you the final remark of this one. Think about this one. Let's say here we have R and R. This is for source and drain. And previously, now let's say that there was 100 R. Good. Now, by doing our own best, we were able to reduce this channel resistance by half. Now, instead of previous technologies 100 R, now we can make a system like 50 R. Then what is the expected increase of our current? Previously, equivalent resistance was 102 R. Now this one becomes 52 R. So when we apply same bias, then we can expect almost twice higher current for same system. Simply speaking, reduction of channel resistance almost 100% reflect the increase of our current performance. Now think about this one. Now we have R. And fortunately, we were able to once again make a huge improvement. Now our resistance is just half of it. So now we have 0.5 R. Wow! Now can we expect twice higher current? Actually, not. Previous we had 3 R. Now we have 2.5 R. So expected increase of our current is just about 20%, maybe. Although we have increased our performance, intrinsic performance twice, but the gain is just 20%. Why? Because it is now limited by this source and drain resistance. Then you can ask me this question: where are we now? Are we in the first example or are we in the second example? Unfortunately, we are currently the era of our second example. So simply speaking, our internal transistor is good, so good, already good. But point is, in order to fabricate it, we must introduce this fixed resistive component, and without improvement of this resistance component, we cannot further increase the performance. And please note that up to now, the main discussion was about finite silicon resistivity. But another one we have to be a little bit careful is source drain resistance has another contribution. So metal contact resistance. So here we have the contact resistance between this via metal and N+ region. There exists this interface resistance. Up to now, I have explained the resistance coming from this N+ region, but here we have the contact, and contact itself introduces certain finite resistance. So sometimes actually this contact resistance gives more contribution to the contact resistance, the overall parasitic resistance. So that is quite really important to reduce this resistance. Of course, in industry, there are experts whose entire career is devoted to optimizing this procedure, so they can try to have even better ones. Okay, so I think that I have covered very important topic, so source drain resistance. And now let's go to actually I have thought about this way. Maybe I have to open another separate semester course for highly matched to this advanced topic, because each of this slide is corresponding to several months long topic. But today I will just mention them. One is hot carrier effect. Please have a look at this left figure. Now here we have a source and here we have a drain. Source and drain. And drain voltage is quite high. Now what happens to these electrons? Everybody understand, when we just draw the conduction band profile, then it looks like this. This is the conventional way we visualize our energy band diagram. So this is a source and this is a drain, and of course here we have the difference, and this energy difference is corresponding to minus Q times our drain source voltage. For example, if we apply 1 volt, then we have 1 EV difference between source and drain. If we apply 2.5 volt to our drain, then there is 2.5 EV difference between source and drain. So now think about this one. For this electron, let's think about a certain electron which can overcome this maximum potential barrier. After that, the destiny of this electron just looks like this. Starting from this position, it just to overcome the barrier, so its velocity would be quite small. Just to overcome that barrier. After that, what happened? So because it can see 1 EV, 2 EV, 3 EV, depending on its applied drain voltage, it can see huge energy difference between its peak point and final destination. So now it can accelerate severely. So usually people think about this one. So when we have an electron, after that, if we keep our electron's energy level and just move it to different position, then its trajectory will just show this way. It means that if we have such kind of a lucky electron, yes, then how can we interpret the energetic state of this electron? This electron, in position wise, it is already in the drain region, and its energy is so high. Why it is so high? Because it does not lose its energy, and this energy is just used as the kinetic energy of this electron. Simply speaking, this electron becomes extremely fast. Many electrons, for most electrons, the situation is a little bit different. Electrons are moving a certain distance. After that, there occurs the scattering event. When scattering event is occurring, then it loses its energy, and its energy level is decreased because it just gives certain energy into the environment, scatterer, and it goes once again. After that, scattering happens once again, and again. So if that continues, when they really arrive at the drain part, actually their final energy would be somewhat lower than the initial injection energy. This is the usual case. So for many electrons, for most electrons, this downhill obtained by source and drain is the way to lose its energy. So many scattering events and giving the energy into environment, and after that it becomes relatively having low kinetic energy. However, think about this case. There is a lucky electron, which is quite lucky, and when it moves, so there are many scatterers comes in and try to hit that electron, but it just escape from here to there, and survive without being hit by the scatterers. Then what will happen? Once it succeeds to arrive at the drain side, it becomes super fast electron, having quite high energy. This electron is called as hot electron. Why it is called as hot? We believe that this kinetic energy, when kinetic energy is high, it is corresponding to the high temperature. From this analogy, say that hot electron, when we say hot electron, it means that its kinetic energy is so hot. Usual expected kinetic energy for our normal electrons are more or less orders of kBT, thermal energy. It is the expected value of kinetic energy. However, in this case, their kinetic energy can be much higher, orders of just Q times VDS, if they are never experience any kind of scattering. So, of course, the number or the probability to become a hot electron is really low. Really low means that not orders of 1 billion, so much lower than that probability. But anyway, if we have hot electron, then this one treated as a special one, because let's think about a Superman or super person who can fly freely. Then there are 8 billion human beings. However, there is one Superman. Then we must pay attention to this guy, because our previous method to localize person, these methods are no longer valid. So you cannot take him or her to a prison, because easily escape by just fly to the sky. So for this hot electron, our conventional treatment is not valid, and we need better treatment for these electrons. So I will continue the discussion about hot electron related ones on next Monday. Thank you.